I am Dr. Paragmoni Kalita from Department of Mechanical Engineering, Tezpur University. I am going to present an introduction to fluids. The outline of this presentation is we'll start with the basic definition of a fluid. Followed by this, we'll introduce the concepts of viscosity, the classification of fluids based on their viscous behaviors, and then the influence of temperature on viscosity. Now, what is a fluid? In terms of a layman, one can define a fluid as any substance that is capable of flowing. But if you want to go more specific, then the technical definition of fluid is that fluid is any substance that continues to deform as long as a shear stress is applied on it, however small it may be. Here, the word small is a keyword. To illustrate this point, we can focus on figure 1, where we have a flat surface shown with the hatched lines, over which there is a fluid having different layers. Now on the top surface, a shear stress is acting. Now as long as this stress acts, however small it may be, these layers will continue to move one above the other, and this continued movement, because of application of the shear stress, is a characteristic of any fluid. Now, because we have realized that the fluids moves in layers and it will give rise to differential velocities across the different layers. Now, based on this, we can define a property called viscosity. Now, what is viscosity? It is the property of a fluid that resists the relative motion among the different layers of a fluid. What we understand by this is that, say again in this figure 2, we have a solid surface. The fluid layers attached to the solid wall will have a velocity of 0 with reference to the wall, whereas the top layer will move at the same velocity represented by the symbol capital U, and this velocity capital U is the velocity of the object that is creating a shear stress of tau. As a result of this phenomenon, the different layers from the free surface till the solid boundary have different velocities, and the velocity gradient is defined as the rate of change of velocity per unit change in vertical height from the wall. This is mathematically expressed by the expression velocity gradient is equal to du upon dy. Now, whenever there is a velocity gradient, there is a relation between the shear stress and the velocity gradient that is expressed by equation 1. Here, mu is called the coefficient of dynamic viscosity, and n is an index whose value determines the type of the fluid. As a special case, when n is equal to 1, the fluid is called Newtonian, otherwise it is called non-Newtonian. Now, based on the motion of different fluid layers due to application of a shear stress, we can classify the fluids based on their behavior called rheological behavior. The major classification is ideal fluid and real fluid. Ideal fluid, as the name suggests, will possess basically zero viscosity, and in that case there will be no shear stress created because the viscosity is 0. Whereas a real fluid, as the name itself suggests, will possess some finite amount of viscosity. Again, based on the viscous behavior or the rheological behavior, these real fluids can be further classified into Bingham plastic, dilatant fluid, Newtonian fluid, and pseudoplastic. Now these different kinds of fluids are shown in figure 3. We can see an ideal solid where whatever shear stress we apply, there will be no velocity gradient created. Whereas an ideal fluid is one where irrespective of the velocity gradient, the shear stress is zero. A Bingham plastic is a substance which doesn't deform till some finite amount of shear stress is applied, and beyond that the fluid behaves like a Newtonian fluid. The best example is the toothpaste. If we recollect, we'll see that as we go on squeezing the tube till some minimum amount of squeezing pressure is applied, the toothpaste doesn't come out, and beyond a certain amount of squeezing pressure, the toothpaste flows out of the tube. Likewise, we can also define some non-Newtonian fluids like dilatant fluid and pseudoplastic. The dilatant fluids are also called shear thickening fluids, and the pseudoplastics are also called shear thinning fluids. The examples of dilatant fluid and pseudoplastic are cornstarch solution in water and paint respectively. As we can see from figure 3, in the case of a dilatant fluid, as the velocity gradient goes on increasing, the shear stress increases at a faster rate. Whereas in the case of a pseudoplastic or a shear thinning fluid, with the increased velocity gradient, the rate of increase of shear stress goes on decreasing, and in the case of a Newtonian fluid, the shear stress is directly proportional to the velocity gradient. And these all are again listed in this particular slide. Again, based on the time behavior of the non-Newtonian fluids, this can be further classified into time-independent and time-dependent fluids. Now, what is time-independent fluid? Now, at a particular velocity gradient, the shear stress, if it does not change with time, then these are called time-independent fluids. Whereas there are many fluids where even though the velocity gradient remains constant, the shear stress may either increase or decrease with time, as shown in figure 4. Here we see that the upper graph shown with a green line, the shear stress, even though the velocity gradient du dy remains constant, it increases with time. This kind of fluids are called rheopectic fluids. Whereas in the case of a thixotropic fluid, the shear stress, it goes on decreasing with time at a constant velocity gradient. And in these slides, we show different kinds of fluids, define them, and we see different kinds of examples. Example of thixotropic fluid is blood plasma or latex inks that are used for our ball pens. Dilatant fluids already we have discussed, is a starch solution in water or titanium oxide. Bingham fluids, examples chocolate, mayonnaise, toothpaste, etc. Now this viscosity, does it have any relation with temperature? The answer is yes. However, the behavior of viscosity for a liquid and for a gas, they are different. This is because of the inherent mechanism of the development of viscosity in liquids and gases. In the case of a liquid, the viscosity is primarily because of the intermolecular cohesive forces, whereas in the case of a gas, the viscosity is because of the intermolecular collisions. Now, in the case of a liquid, when the temperature increases, the intermolecular cohesive forces decrease. As a result of this, the viscosity of liquids decreases with temperature. In the case of a gas, however, as the temperature increases, the random kinetic energy of the gas molecules also increase, and this leads to more vigorous intermolecular collisions, and this gives rise to increased viscosity with the rise in temperature. This behavior of liquid and gas is shown in figure 5. Thank you.